there is some conformal field theory which you might find interesting. And there is some Würzburg-Landau theory and process. That's my sort of qualification for speaking here. So, okay. So let's start at the beginning and say a few things that we all knew in grad school but really haven't thought about since then. If you do band theory of solids, you think of electrons as waves. You think of them as waves, and like all waves, they have some particular modes, wave modes that they can occupy depending on the shape of the waveguide. In this case, the waveguide is just a periodic array of atoms in the crystal, the nuclei. And the only sort of particle aspect you put in is the Fermi-Dirac statistics or Pauli exclusion principle, where you say that no more than two particles can go into a given wave mode, one with up spin, one with down spin. Right? That's how we think. When electron-electron interactions are very strong, it's actually not a great idea to think of electrons as waves. And it's much better to exploit the fact that in quantum mechanics, the same thing can be a particle and a wave. And so it's much better to think of them as particles which repel each other. And if you think like that, you're now not thinking in terms of waves and waveguides, you're thinking in terms of billiard balls that have some charge on them and that want to be as far away from other billiard balls of the same charge.
So you're saying it's better to work in position space than
that's right. So then it's much better to start with the limit where you first find some configuration of charges that minimizes this interaction energy and then put in the kinetic energy effects as a perturbation, right? Do a strong coupling. And that leads to predictions that are often completely the opposite of what you would predict with band theory. And the perfect example of
what was the last phrase? Spin remains dynamically.
Right. So I mean,
thought of as.
That's right. So we'll come to that. So the first point to note is that if you had a half-filled band in band theory, this corresponds to the case where there's exactly one charge carrier per nucleus on some periodic array. Right? Imagining there's only one active orbital. Then band theory would predict that this is a really good metal because half the states are filled. The standard picture is that if you apply electric field, it tilts the lattice, tilts the band like that, and things can flow, right? But if you think in terms of this strong electron-electron interaction, the picture in terms of billiard balls is that there's some bunch of sides on which your billiard ball can go and sit, and there's one billiard ball or electron per side. And any motion is going to lead to some double occupancy. This double occupancy of spatial orbitals would be allowed if the spins are antiparallel, there's no Pauli blocking, but it's going to cost an enormous amount of electrostatic energy. So if you think in this real space picture, you would say such a material can never conduct electricity. Whereas if you think in band theory, it's the best possible conductor you can have after electrons, huge density of states, big Fermi surface, etc. This might be too high. So,
spins remaining dynamic is just that the spins can flip around.
That's
Is this what they call a spin liquid?
We'll come to that. So there are these two differing conclusions, and which one of them is correct will depend, of course, on the strength of the electron-electron interactions. If they are very strong, it's better to think in real space, and this conclusion would be correct. If they are very weak, it's better to think of electrons as waves, and the other conclusion, whether it's a good metal, would be correct. And if it's somewhere in the middle, well, you don't know what really happens, so you do the experiment, and the calculations are very difficult because when you're very strong from both, are very far away from both. So this is the basic.
Sorry,
Yeah.
I really apologize.
Yeah.
Basically, if the electron-electron interaction is very weak, you do the waves.
That's right.
And if on the other hand, say it is very strongly repulsive or
Because of the
something.
particles, and you start in this level, right? Either you do a weak coupling or a strong coupling. If it's in the middle, you don't know what. So that's the background, right? And the spins remaining dynamical is this picture. The point is that although the particles are where they are, in this case, oops, I don't know if this thing works. Okay. In this case, this electron could hop there, and then it has then there's in the next process the same electron could hop back, or the other electron could hop back, and that would correspond to an exchange of spin. So there is a non-trivial quantum Hamiltonian that you have to write down to the spins, even in this extreme limit, right? At least to second order in perturbation theory, you can see how that will arise. This is basically energy denominator for the double occupancy is U, and then there's T, and then T coming back, and there's an effective. And you can work this.
And at zeroth order was degenerate.
Zeroth order, it was actually there was a degeneracy of Dn, where n is the number of sides.
So
And
no matter how
that's
small the interaction was, it's very important.
That's right. So you have to work out the effective Hamiltonian in this massively degenerate term, right? And that's where all the spin physics comes in. So all this business of working with quantum spin models is simply working out first what's the effective Hamiltonian in this degenerate subspace, and then understanding what that does.
In a system where the only degrees of freedom are spin.
In a system where only.
And this is called the spin liquid.
No, this is just the spin Hamiltonian, right?
That's a particular kind of state.
So now all the physics will be at energy scales J, which are T square over 2, not at energy scales of the Hawking. Okay, so we are looking at that part of the spectrum at those temperatures, right? And then the question is, what do the spins do, right? So first of all, what does this Hamiltonian look like? Well, the picture I drew gives you basically a term like this, in the simplest case where there's one active orbital per side, and this is called the Heisenberg exchange. Because if you write down the operator Bij, which is 1/4 minus Si dot Sj, it's actually the operator that exchanges the spin liquids, right? So this is just some constant shift of the exchange operator of SU2. So this is the Heisenberg spin exchange, and at least in the simple calculation you do, J will just kind of come out to be 4T square over U or something like that. It will be positive. Okay? And so J is going to be big and positive in this way of thinking. But that's not the whole story, because this is some very artificial boundary where there is one active orbital at every side. The real physics is more complicated. You have to worry about the actual quantum chemistry of the outer orbitals and do the perturbation theory in that language. And when you do that, things get a bit more murky. There are different energy scales that compete, and so you don't in practice ever try to compute the values. You almost never can do a reliable enough computation of the value of J. This is perhaps my prejudice because I don't know methods that do it. What you can do is extract the values of J from experiment, and that can be done fairly reliably if the energy scale of J is small enough that an external magnetic field can be applied that actually completely overwhelms the system and polarizes all the spins along the field. If you do that, the Hamiltonian becomes the perturbation, and the state is just dictated by the external field. It's everything pointing in one direction, let's say the Z direction. So you then start with a state that's all up, and if you fire neutrons at this, the neutron magnetic moment interacts with these, and there can be inelastic scattering, and in the process one of these guys will get single spin flip scattering. And what you will then really map out, if you did that and measured the energy with which the neutron went in and came out, you would get a spectrum of single spin flip scattering in this limit, in the fully polarized limit. And now the Hamiltonian is the perturbation, so you can just do perturbation theory in the Hamiltonian and ask what is this spectrum. And the spectrum will be some functional of all the J's in the system. Then you just fit.
Could your J turn out to be a function of your H?
Not in this simple-minded way of thinking. Right? No.
It's a complicated material, its properties get modified when you add it.
Well, remember, this is T square over U. So I only need to go above this energy scale to own spin interactions. And everything else happening is at much higher energy scale in the beginning. Right? It's electron volts versus Kelvin kind of distinction. Right? So typical value of J might be 10 Kelvin. So 10 Tesla field is good enough to polarize it.
But for ITC, this cannot be done very reliably.
No,
right?
no, that, like I said, only when J is of order accessible magnetism is the point I was making. Only in those cases is the value of J known precisely from experiment. Because there is no other experimental handle on this number that is reliable enough. In all other instances, you have to put some theory, and that is where things get complicated. And you have to argue about what is the theoretical calculation you did to predict the values of J. You might not be in the extreme strong coupling limit, and your second order perturbation theory result may not be very reliable. And so then this is where the uncertainty comes in. But for the purposes of this talk, I'm going to take J as a given, either computed by some black box method that people claim to have control over, or measured experimentally, inferred from experiments. Right? Yeah.
I'm really sorry, you said it
Yeah,
right.
yeah, yeah.
So to measure J in a situation where you have this separation of
Yeah,
energies,
yeah.
you turn on a magnetic field,
That's
everything's aligned, and then you check the gap in energy between
So
that state
then
and
you
some
ask in this
nearby
limit,
exciter.
yeah, so what you do is you take this limit where the magnetic field is bigger than J,
Correct.
and then the ground state is just all of it.
Yeah.
And you ask what is the spectrum of excitations. Now this is an exact eigenstate of the system, although it's a very high energy eigenstate of the original. Now it's become the ground state, you pulled it down. Right? Now you ask what is the spectrum of excitations, you can work that out perturbatively in J.
Yeah. Some spin wave.
It's exactly, it's the single spin flip excitations. They'll have some band structure.
Yeah.
So in effect, the values of J become the parameters of the band structure for this single spin flip particle. Think of this as your particle, and there's some band structure.
You can measure the magnetic susceptibility at high temperatures with just
That
theory-wise.
yes, but that just gives you an average number. What Vishwanath is saying is you could just look at plots like this, chi inverse versus temperature, and at high temperature it's a straight line. But it's not, unless there's absolutely no interactions, it's not a straight line passing to the origin. It's a straight line with some intercept, right? And you look at that intercept, that's, so basically you're saying that chi at high temperatures looks like. So there's some single number theta that this gives, which is somehow the average value of the J's. Not enough for us to actually do a theoretical calculation of what the ground state could be and things like that, but the scale of J is reproduced by this. And the sign of J tells you whether the dominant interactions are ferromagnetic or antiferromagnetic. That's right.
So just to understand again, so there's a certain scale of energy associated with the magnetic field. This is higher energy than the splitting energy, right?
That's right. This J square or T square would.
But a lower energy than just
E or U. Yeah. Both of them are much bigger. They are measured, T's and U's are measured in electron volts. Right? Whereas J's are measured in a few Kelvin, 10, 20, 30, except in in certain oxides where there can be, again, 300 Kelvin, 400 Kelvin, things like that. And typically they are like 100 Kelvin.
and therefore this H is a small perturbation of the underlying
That's right. That's right. That's right. So we don't expect it to have orbital effects that
Yeah.
change, for example, the atomic orbitals. That's right. Okay. So, yeah.
It's only nearest neighbor.
So this is just the simplest thing that you get to leading order in perturbation theory in this simple example where I had one orbital per cycle. Of course, there are, if you now carry out this strong coupling expansion to higher orders, you get multi-spin interaction effects, you get further neighbor couplings, you get everything that many hops can give you in the strong coupling expansion, right?
So you can make some kind of an RG argument to say that those are not.
No, they actually can play a big role because these things lead to simple states, and those other effects, if they are even at the 20-30% level, can try and make the energies of these simple states bad, and some other states can become competitive. So then it becomes a competition between. So we'll come to when those effects may matter more. Right.
So,
Yeah.
is there actually someone by the name Good Enough?
This is the you're the first guy to get the pun. I always put this slide up and everybody ignores it. But it really is just a good enough explanation for us. It's quite remarkable that the guy who came up with the thumb rule as a name which is good enough.
This is initial A.
Sorry. That is it's clear. Yeah. Yeah, so there is a thumb rule to actually saying whether J is large or small and whether it's positive or negative. And those rules were sort of written down in this textbook, but they go back a bit earlier, I think. They go back to work of Anderson and Rajdeep will know more about the exact origin. I mean, are these co-authors in a paper? I don't know. Or they separately do it. I think they separately do it. Yeah. So there are complications to this simple Hamiltonian. And they have to do with spin-orbit coupling and to do with orbital degeneracy. So your electron may actually have a choice of nearby orbitals to sit in. At the atomic level itself, that splitting may not be very big. So when I say an electron is at some site, that may not be a unique statement. So then there's more degrees of freedom to include in your strong coupling expansion, and things get quite hairy. And for example, Shubhro's invested some time, and so are many other people, in trying to work out what the analog of this is for much more complicated systems with spin-orbit couplings and multiple orbitals and so on. But I won't go there. if you had a bipartite lattice on which you had these single orbitals, in the simplest possible example, then an exchange interaction of this kind has an obvious semi-classical ground state. Right? You just take bipartite means the nearest neighbor connectivity is such that sites of one type only have neighbors of the other. Right? So then square lattice, cubic lattice, any hyperthermic lattice, right? And so in that case, there's an obvious way of minimizing this energy. You just take all the spins of one sublattice to point somewhere in spin space, and the other sublattice points exactly opposite, right? And that's a good classical ground state if you think of this just as unit vectors. And it's unique up to global rotations, right? And so then the question at least has a starting point. You could then try and understand if I stop thinking of spins as classical unit vectors, but try to put in the quantum mechanics, let's say in a 1 over S expansion. Don't think of them, imagine they're not spin half but spin 100, and ask whether up to order 1 over 100 is this guy. That's spin wave. So you can do that, and you find that even on the square lattice, that simple arrangement is stable. It gets less stable in lower dimensions, but on the square lattice it's already stable. In one dimension it's not stable for obvious reasons, but having to do with the moment one. But in 2 and higher dimensions it's stable at zero temperature. So we know what happens at low enough temperature in such cases. Right? So that ordered state is called the Néel state after the physicists who first talked about it.
Sorry, you said it, but we'll start with the large S sort of
Yeah.
thing, and if you say numerically or whatever, try to come down to
Right.
S of half or
Right.
whatever,
Right.
it still is pretty good.
Right.
Say
So you get a
2D.
prediction in order 1 over S, and then you can do in these kinds of problems where it's bipartite, straightforward quantum Monte Carlo simulations of the quantum mechanical spins, and you find that although the value of the Néel ordered parameter is misrepresented by maybe 20%, the fact that it's long range order is in fact, even the correction to the value of the Néel order parameter is not huge. It's maybe 10-20%.
And large S gives you a systematic kick.
Right. So large S is simply the statement that I write Sz as S minus the number of some bosons, and S plus as I guess E dagger, and S minus as, and this to the given order reproduces angular momentum commutation. You can fix it, you can make it more systematic, but this will be enough to get leading order results.
Yeah, and roughly I'm thinking of it as in the action, everything is order S.
Right. So in fact, what you're saying is that the classical answer is order JS,
Right.
and then you're trying to see what's the JS term.
Exactly. So it's the usual situation. that
Usual
happens.
situation. Exactly.
Sorry, so Mermin also said that 2-dimension
Yeah. So, but I'm talking
Plus
ground
one.
states. Talking ground states. Right. You're right. So experimentally in a two-dimensional magnet, what you see is that the ground state wants to be long-range order, but of course at non-zero temperature it's not. So the correlation length for Néel order is some exponentially large object in temperature. That's what you see. So that's correct. That's it. But at the level of what the ground state of the quantum mechanics problem is, it's long range. So now we come to this notion of geometric frustration, which is sort of where things get more interesting, because you can have situations where this leading interaction J, that's the nearest neighbor Heisenberg exchange, which is antiferromagnetic, basically gets quenched out. It can't pick the ground state. And the simplest way to understand that is just take a single triangle, right? And for the moment, imagine that you want to make an Néel ordered state. It's not just that's going to be picked, but if you wanted to make an Néel ordered state, you have to pick an axis, point something along the axis, something around perpendicular in the opposite direction, right? Parallel and anti-parallel. So we point this along the axis and that against. This spin doesn't quite know what to do. So this completely is going to. So this suggests that lattices with triangles in their nearest neighbor connectivity matrix will not want to make this simple Néel ordered state, because things get confusing. There's a huge degeneracy if you insist on collinear schemes. So what actually happens depends then on the lattice, depends then on how these triangles actually make the big lattice. Right? So before we go further, I should just immediately say that if you actually had just a triangular lattice, which we are going to talk about later, so just a lattice of triangles like that in 2 dimensions, just the triangular lattice, regular tiling of the plane with edge sharing triangles, Then there is again long range order. You can show this again in a 1 over s expansion, but now you do 1 over s about a different state. The state is the coplanar 120-degree state, like that. So you notice that the triangular lattice is tripartite, A, B, C decomposition, and you say all the A spins point, let's say here in a plane, and then the B point there and the C point there. This arrangement is the one that has a stable spin wave theory around it. Fluctuations when you include, they don't seem to destroy it. So you would say at the level of order 1 over s corrections that this is the state that will get picked. And again, people have good evidence. Here the evidence is not so great because you can't do straightforward quantum Monte Carlo, but there is good evidence that this is indeed the ground state of the nearest neighbor Heisenberg antiferromagnet on the triangular lattice.
But they're still coplanar, isn't it? I mean,
Coplanar. So what's happening is that the system is spontaneously picking a plane, and then it's also spontaneously picking a direction in that plane. So it is spin order.
So largest, first thing you need to show is that just classically this is the configuration.
That you can, yeah, so that you can show.
That you can show.
And then you can show further that the 1 over s corrections are sort of not doing anything odd.
Yeah.
So the structure of the Goldstones is a little bit different, quite different.
No, actually, because you're again picking
One
one axis.
One axis, but then there's a plane business, there's a preferred plane also.
Right, but no, but once you, yeah, so that's right, because there's 3 sublattices, you're actually picking 2 directions.
Yeah.
That's right, which are 120 degree apart. That's right. So you can work out the spin wave modes for this structure, right? And you can see. So you're right. There's in plane and out of plane long wavelength modes which are different. That's right. This is actually the simplest example of what is a spiral state, and in any spiral state, this is true. There's in plane and out of plane.
So you're thinking of 3 dimensions.
I mean, spin space is 3 dimensions.
Oh, I see.
Yes, the ordering is only in some
That's
preferred.
I see. I see. Now I understand.
So, but if you didn't have this, so this happens on the triangular lattice. The question is what happens on other lattices? What you can generally say is that in many cases, this sort of frustration leads to a quenching of the degeneracy. So it's no longer able to pick the ground state. And then that's interesting because anytime the leading big term in the Hamiltonian can't pick the ground state, all sorts of interesting things can happen because of the competition between subleading effects, because of quantum fluctuations and so on. So that's why this is interesting from a theoretical point of view.
So, one generalization that you talked about was sticking to the spins belonging to SO3 and taking the high representation.
SU2 and high representation. Yeah.
Let me say SO. Yeah.
Spin half, spin
Yeah.
quarter. Yeah.
But another generalization would be to stick to the same representation but generalize SO3 to SON.
No, but that's, I don't know what.
It may not have physical meaning.
Right.
But just as a
yeah.
mathematical model.
Sure.
So will that also give you something? I mean, that
no,
something to be tractable that large end.
Yeah. So in fact, if you know that, if you're looking at finite temperature physics, where the quantum mechanics is not so important, that's often a very good tool. So then you don't really worry about the quantum mechanics of the spins anymore, right? You have some directionality, and that's all you care about. Then you can go to that kind of a large limit, and it's extremely useful. But that's usually the case for thermal effects, thermal transitions, not ground state.
You're saying different SONs in the ground state physics will have very different physics.
Right. That's right.
Nice. SO4 will be very different.
Very different. In fact, I don't know if you remember, Vibhur Kaul was visiting last year and he talked about some SON models which behave completely differently from ICP. Okay. So let's go ahead. So the other point to note by way of background is that there's an enormous number of materials.
Can I just ask something?
Yeah.
Down,
Yeah,
which
go
is, so if you take other lattices, it seemed from what you said that if you had, like here you had an obvious 120
That's right.
degree
That's
symmetry.
right. In other lattices you may not.
You may not, but
That's
at
right.
least lattices which have similar, like instead of
Yeah.
bipartite, you have 3 sublattices,
That's
you have
right.
n sublattices related to symmetries.
That's right. So you
This
could
may
try and
work in
construct
larger-
classical ground states, and then you could ask, are they stable or not? But the point is that the triangular lattice is sometimes kind of misleading because it's a special case where the obvious classical thing is actually stable and everything is good. In many other spin half magnets with Hardy lattices, what you write down classically, there's a big difference between largesse and spin half. This is so sort of the way to say it is quantum fluctuations actually matter much more when you have frustration.
So that might mean that the largest is not a good limit.
That's right. Yeah, that's exactly right. That's exactly right. So you have fewer handles on what actually happens. That's right. So the other point to make then is that there are lots of lattices with triangles in the nearest neighbor connectivity matrix. And by this I mean, there's all sorts of other atoms in the crystal structure.
Sorry, just to say again, SI.Sj in group theory terms is just some difference between Casimirs. Right? So the Casimir of the group, the representation, you couple the two minus the Casimir of the individual representations by 2.
Right.
So just to say, I don't know if it's of any interest, but so there's a natural generalization of your model just to any group in any representation. And
So I could also say that SI.Sj is just the dot product of generators on two sides. And so I could just write down something like G mu nu at a side, G mu nu at some other side, sum over, right? Something like that. That's also, is that what you're saying?
Yeah, I'm saying this you can write as J1 plus J2 the whole thing squared
Yeah.
minus J1
That's
plus
right.
J2
So
squared.
you want to generalize it
Now,
that way. Yeah, okay.
just in case it's of interest, this can then be generalized to, this basic model that you have would work for any group in any representation.
Correct.
And I wonder if you could learn something by just by enlarging your
Right,
group.
so that's exactly the kind of
more general.
So for example, people have looked at models like this with SUN, for example, and then you have a choice. You have to decide what representation of SUN you will put on each lattice side. If you have a bipartite lattice, there's one simple answer. You put the fundamental representation on one sublattice, and the other sublattice to which it talks, you put the complex conjugate of the fundamental. That's an easy choice to make, because then you can do some simple computations. You can make other choices. You can say you will put the fundamental on every side. On the triangular lattice, for example, that's been studied, and people have studied SU3, SU4, SU5, and all sorts of funny ground states arise as a function of
It's a very rich physics and very
yeah.
particular.
In fact, this is an industry, as you might expect. And in fact, it's also an industry to ask which of these cases can be studied computationally without this famous Monte Carlo sign problem. Right? And so, for example, Ripu has realized that if you take SON with some particular representations, you can actually study it in a sign-free way. I mean, it's one of these curious things where you actually start with the algorithm you have for SU2, and then you just blindly use it on some non-bipartite lattice, and then you ask, then it works, it's some StatMech problem which you do, but then you ask what interpretation it has in terms of a Hamiltonian, it turns out to be SON. So, things like that.
There seems to be no reason to expect a sign problem on the face of it, right? Because it's just bosonic spins.
No. So bosons can have sign problems very trivially, right? If the sign of the hopping matrix, so if you have any off-diagonal operator in your Hamiltonian with a positive matrix element, then in the trace e to the minus beta h, imagine doing a high temperature expansion. It will give you minus signs, and those minus signs better cancel in pairs, otherwise the overall sign of the configuration is gone. And so in fact, that's the whole problem. So this doesn't have to do with determinants, the way fermions.
That's what I
It has to do with something simpler, but equally interesting. Right. So among the lattices that people have studied, many of these, by the way, materials start out as being minerals that have been known to geologists for literally 100 years, but people have only recently understood that they have interesting magnetic properties. So they have funny names like cobalt-smithite, columbite, paramagnet, things like that, which are, because they are minerals, they have been named like that. But they are basically oxides of transition metals or rare earths. And the transition metals carry magnetic moments and live on a lattice, which if you just looked at the transition metal magnetic moment, makes lattices with triangles. So among the lattices that are made are these sorts of corner sharing arrangement of regular tetrahedra that fill up space. This is called a 5-floor lattice. You have triangular lattices, of course. You can have multi-layer triangular lattices and then interrupted by some non-magnetic charm. So quasi-two-dimensional systems. You can have corner, so the two-dimensional analog of this would be corner sharing regular triangles in a network. That's called the Kagome lattice, and that often arises in materials. And so there's a whole zoo of these possibilities, and a lot of people have done a lot of work trying to understand specific cases. And so the other point to remember before I move forward is that although I talked so far about JS.S, this single and anisotropy that picks out an axis in spin space can actually be very large. And this comes from spin orbit coupling, because the spin you're talking about is not really the quantum mechanical spin, it's the quantum mechanical value of J in the ion, L plus S. And because there's an orbital part to it, this is now sensitive to varied quantums. And so there's the interplay between the orbital structure, that's the L, and the final value of G. And so, although you're writing it in the language of spins, you have to sometimes go back and remember that it's J you're talking about. And then there can be very strong spin orbit coupling effects, which lead to anisotropies in the spin orbit. So there's not a pseudo-symmetry.
So like an effective background magnetic field.
Well, not an effective background magnetic field. I don't know of a case where that happens. Although I know cases where there are background fields that oscillate in a particular way on the lattice. But those background fields actually couple J1 dot J2 cross J3 type.
But no linear in J.
No linear, yeah. But the simplest one is things like minus Jz square.
Okay.
You know, pick an axis which is favored over other axes, or pick an axis that is disfavored over other axes. Right? That's the simplest.
We have a spin orbiter because crystal field is also reviewed exactly that.
Yeah, but the spin would be blind to crystal fields if G
Had L not been.
That's the point. Right? I mean, there's always crystal field effects, and in fact, the value of the spin orbit coupling is determined by the nature of the crystal fields, of course. But the spins would know nothing about it without spin orbit coupling. So if you have a magnetic ion which has no L in its ground state, then it's not sensitive. That's it.
Crystal field is just being charged, electric field.
It's just electric, yeah. Electrostatic potentials affect L, and when the J you're talking about has the L component, then it's right.
The electrostatic field produced by the lattice.
Neighboring ions.
Neighboring ions.
Which are not typically not magnetic.
That's right.
So I guess just to understand that, so the point is the crystal itself breaks rotational invariance.
That's exactly. So L is no longer what you're looking at. You're looking at the the correct things to do with the point group symmetry of the crystal.
Yeah.
So that's why it becomes square.
For example, yeah.
On the average, there's no way.
That's it. That's right. So there's a large number of examples where the anisotropies are actually larger by even an order of magnitude of exchange. And so these are really what, so if it's single ion anisotropy of this kind, then along this axis you can really think of Ising moments. So the Ising model we like when we read StatMech actually becomes the correct way to think. At least some souped up versions of it become the correct way to think in these models. Right? And you can play this game where you systematically do an expansion in J over 2 to see what are the next effects, right, beyond the Ising model. And that's not our focus today, but we had a lot of fun earlier with our Arnav's and his thesis doing exactly that for a bunch of systems. And you get a very nice sort of global picture of what happens.
So in particular, you can, in the limit of large T, of course, the system is very simple,
Right.
and then you can try to go towards the frustrated
Exactly.
case and
So
see.
J is the frustration, and you can put it in very systematic. And you can ask.
You
what-
get phase transitions and
Yeah,
so on,
yeah,
the ground
yeah.
state changes
Yeah.
in dramatic way.
Yeah, and you get unusual terms which are, so you can, if you think of just Ising models, if you just think of Ising models, you're used to writing down things like the energy is some J, sigma, right? And if you ask how do I put quantum mechanics in, you might say, well, just put something. But when you actually do the systematic strong coupling expansion and ask what's the leading quantum effect, it's actually more unusual terms. And so you need to sort of ask what they do. We all have a good intuition of what this does, but that may not be the right way to put quantum mechanics into this. So then you can sort of do it very systematically and ask what it is. So that's something.
D can be of sign also.
Sorry?
D can be of either sign.
That's right. So you can have easy plane as well. And that's a whole other zoo because then you've got an XY model classically. And that's already quantum mechanics. Because, you know, unlike easy axis, where now you can think classically. Easy plane, there are two non-commuting operators at every side, it's already quantum mechanics. And so it's hard in that sense.
So when you do this last perturbation theory, so
Yeah.
you have the biggest term is the external magnetic field. and
No,
then
the biggest term is not Excel, it's
crystal induced or
So,
whatever.
but so how? Oh, you just have that, and that
That.
itself is.
That says that I should look in the Ising
So
subspace.
that you can, I see that you can handle classically, and then I see.
Yeah, so that just fits the configurations you should look at. They are the fully polarized plus S or minus S right? And then you do degenerate perturbation theory in that 2 to the n dimensional equations. Okay, so the last general point is that when you have anisotropies of this kind, in particular easy axis, the effect of frustration is amplified. And I have actually already said this in some other language. When we had spins that could do what they like, for a single triangle they made a 120-degree state, which is unique. But if you told them you have to point along some axis, they don't know what to do. It's not unique. Right? So this actually amplifies the effect of frustration and makes things more frustrated.
The Ising model is very frustrating.
Very frustrated compared to Heisenberg's spin.
Yeah, because classically you can
Exactly. More degrees of freedom. More stuff you can do to find a minimum.
there's a classical lowest energy state. There's no Ising lowest energy state.
Exactly. So that's the other very simple point.
But in principle, it could so happen that you have some triangular lattice like this, and
Yeah.
you take all possible choices for this question, and then
Yeah.
all of them are very closely lying.
In fact,
downstream to
that's
something.
right. That's exactly right.
But
And
that may
that's
not be classical then. Maybe they're not.
That's right. So we'll come to that in 1 minute. That's exactly what I want to do next. Okay. So let's start exactly with what you want to do. Okay. Let's start with this, which was first looked at by Bonnier, and I think there's parallel work by, I don't know how to pronounce this name. But this is parallel
I
work.
didn't even know about
Yeah,
that.
so it's not, we always call it Bonnier's, but it's there's a second person who did some of this.
I think we actually got up all the correlations correct first time. Before
No. Before Stephenson.
At the same time, it was in
Is
some
that right?
European journal and Stevenson.
Okay, this I didn't know. I knew we had done the partition. Okay. Alright. So anyway, this is generally called 1 year's triangular lattice model, and the history is that Onsager had called the 2D icing model. And there was a question about how generic that solution was. And 1 year put it on a different lattice. The solution went through. Solution goes through for any planar graph. And asked what happens, and then he found a big surprise. Well, at that time, I guess it was a surprise. He says it was. I think he found that there's no finite temperature phase transition. So I'm talking of this model. But I got to this the way I was telling you. I started here, and I just said D is very much larger than J, and I'm now taking the 0th order term in this perturbation.
Spins are all either up or down.
That's all, and it's
It's just Ising model on this lattice.
on this lattice. That's all.
And the lattice is triangle.
Lattice system. Okay, so that's what Bonnier looked at, and he didn't bother to justify it starting here.
So this is somehow because of the extreme crowd state degeneracy.
Yeah, this is just saying what is at least the 0th order term we should understand. That's the classical line.
Yeah. But I'm saying that the lack of phase transition is because of
Exactly. So he found that there's no.
always disordered in a sense.
It's always disordered, and it's even more interesting actually. So first of all, let's answer Gautam's question about how many choices there are and things like that, right? So here, so how many configurations do you have that all have the same energy, right, and are all ground states of this classical problem? Well, you can draw pictures for it in a nice way by noticing that all such configurations must have exactly one bond on every triangle, which is of this type. So on every triangle, there's exactly one bond where the spins are parallel to each other.
they don't want to be.
They don't want to be, but they
But
have to. They have to be. So they pay a price here, and these are the good bonds. So there's one frustrated bond and two unfrustrated bonds per triangle. Now you ask how you would tile the triangular lattice with this restriction. And the right way to do it is, the nice way to do it is to draw the dual lattice, which is the honeycomb lattice. So draw the honeycomb lattice like this. And the triangular lattice sides sit here, right? And so the statement that there is one frustrated bond per triangle corresponds to the statement that from any point of the honeycomb lattice, the graphene lattice, there is exactly one hard rod that emerges. So the hard rod can be here, there, or there, right? And so you now have to cover the honeycomb lattice with these rods or timers, such that every side is touched by exactly one. Okay? And that is a classical counting problem in combinatorics called the timer model. And so the ground states of this problem are in 2-to-1 map with this. 2 because you have to pick the orientation of one span. Right? And then
There are two kinds of hard rods, right? Plus and plus and minus and minus.
yeah, that's the 2. Yeah, 2-to-1 mapping. Right? So we are not worrying about whether it's plus and minus and minus. So we just write like a dot. So then when you fix the value of one speed anywhere in the system, the whole configuration is specified if you knew the diagram. So that's the 2-to-1. And what Stephenson, so 1 year solution is soon after on-factor, right? 1950 odd. But it took another 15 years roughly before people could calculate correlation functions in the low temperature. Because as you know, when you do these exact solutions, calculating partition function is always much easier than calculating correlation function. So in another 15 years, people developed techniques to do the exact calculation of the correlation function. And there's some Pfaffian methods for doing it. And the answer was this. Okay. So what this is saying is if R has coordinates x, y, and I'll write my coordinates like this. This is x, and I think 60 degrees apart is y. That is y. Like that. So two vectors 60 degrees apart is x and y. If it's 60 degrees apart, it will be x minus y. 120 degrees apart. So two vectors 120 degrees apart is x and y. So this is x, that's y. X, y. And you agree to measure triangular lattice coordinates using that coordinate system. Then you get this cosine 2 pi x plus y by 3 with a square root r at the bottom, and this much faster decay. Important thing is that even in the zero temperature limit, this is the answer exactly at zero temperature. At any non-zero temperature, it is this with an exponentially large correlation length on the So this is the dominant decay, it's an oscillating decay, and this is the subdominant power law, which is uniform.
And it's far from rotationally invariant.
It's far from
even in the
yeah, it's got this. Yeah. Okay.
So this was an analytic calculation.
This is using some complicated calculation. You know, this is following Onsarga's methods and using everything you can. Okay. It's really an amazing paper. And you're saying Guttapel did the same thing.
Guttapel also gets something out of, he says that it doesn't order even at zero temperature. I'm not sure about the code.
Okay. I think the fact that it doesn't order is known, for example, from thermodynamics, right? So maybe that's correct. Yeah. Okay, so let's try and understand this result with a little bit of background, and let's do it the way more lazy people would do it without knowing what Pfaffians, determinants, all this.
And just to be totally clear,
Yeah.
if there was some sort of ordering, you would see a piece of the correlator that didn't die out.
That's right. That's exactly right. So if you just saw the cosine without the 1 over beta, that would be non-zero.
Yes.
Right? Or just saw the A without any 1 over R, whichever. And we'll come to that. So let's try and understand this a little bit more heuristically, but I think in a way that gives more insight also. So this part, I was a little lazy and I didn't make transparency. So let me try to do it. So first let's talk about the timer model, because if you want to just work at zero temperature initially, at least that's good enough. We don't need to worry about the speeds. So we won't worry about all configurations of the icing theory, only those that satisfy this condition. So that's the timer. So let's draw.
Only satisfy the constraint that S is either SZ is +1 or -1.
No, that is anyway there. I'm saying doesn't satisfy this ground state constraint that there's only one frustrated bond per temperature. Right? We really want to look at zero temperature and understand Stephenson's.
So you want to identify the Ising spins as some kind of linear combination of scaling fields of different animal positions.
So in your language, the icing spin is going to be a vertex operator of a 2D free boson theory.
So that you get both 1 over root r
Exactly.
as well as 1 over
Exactly.
as well as this cos.
Right. So in fact, to sort of go ahead, sigma is going to have one term which is e to the I phi times some scalar field, and another term, and this is going to have an e to the I q dot r in front of it. That q being the thing that gives me the oscillation 2 pi x plus 1 by 2 is that one. And then there's going to be with some coefficient I don't know. And then there's going to be another term which is e to the 3 I phi. Without any oscillation. Nice.
H is a free boson,
H is
and pi is 3
pi
pi
is pi.
4.
Yeah, pi is pi. Okay. So I will try and convince you of this.
It's a periodic free boson.
Yeah, period. It goes on period 1.
And sorry, what did you say that, so you're just going to look at the timer model,
Yeah.
but
That's why I'm only looking at the dimer model, because I only want to look at the spin problem, the icing model at 0 depth.
That's it.
Right.
So you're saying that the lack of rotational invariance comes about in the observable rather than in the theory. That's really interesting.
It comes about in this. I may not be able to give you a derivation that sort of is rigorous, but I'll indicate you where it's coming from. That's
Presumably the underlying reason is that the Hamiltonian is breaking, at least it breaks rotational.
right, but you could argue if the action, the effective action is grad H square, then the energetics is not remembering that triangular lattice, but the observable is remembering.
Yeah.
That's it.
But I mean, your Hamiltonian, for example, had a term SZ square, right?
Yeah. No, so that's spin space.
That's spin
That's spin
space.
space. Now we are asking about just two-dimensional rotational invariance in the real space plane, which is broken down to the triangular lattice symmetry of the microscopic model.
Yeah.
Right?
So even there, you at least have that breaking down.
Yeah, we have it. But it will turn out that the effective action, the energetics doesn't remember it much. Because all terms that actually remember it will be irrelevant at this fixed point.
So it will remember its sum, right?
Right, so when I write grad H square, it's always plus dot dot dot. The dot dot dots all know about the triangular lattice. I'll show you actually explicitly, but they are irrelevant.
But it remembers it only in that the thing that you measure
Yeah, that has it.
has it.
Because all the other stuff is irrelevant, you don't need to worry about it at the fixed point you're looking at. But this operator, you have to take what it is.
I think that's very interesting because when I saw your result, I thought that means you can't use conformal field theory. It's not
No, but it's in the operator. Yeah, that's in the operator.
Yeah.
So I think this is the nicest way to understand sequences. Personally, I think that is the case. It's kind of, yeah. So let's try and do it. My version of this understanding is incomplete, and unfortunately I don't have a reference where it's done, so I don't know if there's a better way. But there may be a way of doing. So I'll tell you something, and there may be a way of extending what I'm saying into a proper calculation, but I don't have it, and I haven't seen it.
But other operators would not be allowed because they don't respect symmetries, or
You'll see, actually, we'll see that. So let's start now. Okay. So first of all, we have this constraint that one diamond touches every point. So we can write this as saying, add up all the links that belong to a site. Right. Now the site is a honeycomb lattice, right? So let's write it as capital. And this is the diamond number 1 or 0, and this must be 1. That's our constraint.
One diamond touches every, what was it, vertex?
Every site, every honeycomb lattice. Yeah. Right? So we have this. Now this is an unfamiliar form of constraint. It's a sum equal to 1. There's a simple way of, because this is a bipartite lattice.
So now your partition function is just summing over all distributions of dimers that satisfy this constraint with some, with no weight.
That was the point. In fact, I should make the comment that if you actually honestly did this J over D perturbation theory in the original model, then sometimes for large spin, if you are starting with spin S, which is let's say more than 3 halves in my design, then the leading effect of this perturbation theory is actually to give weights to dipole constraints.
I see.
So, and you can work out those weights. They have a very non-trivial form. They make it an interacting dipole.
And at some point you tell us what the spin operator is in terms of the
That's going to be the well, yeah, exactly. So let's convert this constraint into something that looks nicer to our eyes. The way I do that is I say every dimer talks to one A and one B sublattice. It's a bipartite.
So just to be clear, what R is what?
Any point R.
R is summing over the sites.
No, I'm saying for every link.
every site R,
Every site R
is constraint.
has 3 links. So I'm saying you sum over the 3 links that belong to R. Right.
For every R you have to.
For every R, this constraint. So for all R. Right.
R are the links touching the site.
R is the site.
L are the links that touch it.
Yeah.
Thank you.
Okay. So let's make this look nicer. And the way I do that is notice that each link talks to one A and one B. So there's a bipartite decomposition. I can write it like that. Everywhere, right? Then I can say there's a magnetic field, a lattice magnetic field, right? Which is a vector that points from A to B. Okay, so there's a vector that points from A to B, and it has magnitude, which is NL minus just rigging this up so that now if I take the lattice divergence of this guy in this lattice way of taking, let's define B to be on these links, and then there's an obvious definition of the lattice divergence. So you can check that the lattice is completely equivalent to the statement that somehow
NL is either 0 or 1.
NL is 0 or 1, but for this to work, that's not needed.
Are you trying to write it as a DC?
I don't want to call it that, but yes.
But ERTP doesn't seem to be one vector, it seems to be three vectors.
No. So whichever link I'm on, for every link, this is true at every link. So I define a B field that lives on links. And I'm telling you its value. Its value is it always points from A to B along a link, and it has a coefficient which is NL minus 1. So it can point from B to A if this number is minus something.
Yeah. You're just saying the net flux out of every point is 0
That's
because
all.
of the minus 1.
That's right. That's right.
Okay.
So this is 1 over coordination number. You could do this on any point for any time. Okay. So yeah. So this much is good. So now I know how to solve this constraint. If I forgot the fact that NL was 0 or 1 and it was just some real number that obeyed this constraint, I know how to solve this. Right? I just take the two-dimensional version of the curl and I can write P is epsilon mu delta mu of some field H that lives on these triangle sides. H is defined here. P was defined here, here, and here. Right? So dimers live here, here, and here. H lives on the same lattice that the original spins lived on, but H is not yet anything to do with the spins. So this is sort of the next step. You would write this. Now, so far you've not put any physical input into this, right? Which is just rewriting things.
You have to say how the B couples to the IDC.
Right, so that comes later. But first you have to say what's the partition function in this
But
language.
H is a real number or it's
H is a real number. So if this was just real numbers, with no constraints, this was a real number. But H is, N is 0 or 1. But I can still construct an H. I can give you the constructive procedure. That might be more satisfactory than algebra. So here's the construction. So pick any triangular lattice right, put height 0 there. Okay. Now the rule is, if you make a this is called anti-clockwise. If you make an anti-clockwise circuit around any A, if you cross an empty link, you go down by 1/3. So from 0 you go to minus 1/3. Right? Let's say this link was also, then you will again go down by 1/3. This will become minus 2. And then there's a dimer here, we go up by 1/3.
So H now is discrete with units of 1/3.
That's right. Okay, so this is a constructive way of getting this height. Good. Okay. And notice that if the dimer constraint got violated, supposing this also didn't have a dimer on it, we would have a vortex. H would not be simplified. Okay, so we'll come to that.
And the initial choice of H at this point
Pick any side, any one side
as well as derivatives.
That's right, exactly. Right. So that's the constructive way of doing it, but if you want to forget the fact that it's 0 or 1, you can just say P is epsilon mu mu T mu H. Right. Now, so far there's no input, I can just go from IC configuration to dimer configuration to height configuration. All constructively, right? Without sort of doing anything. So here's the physical input now. And this is the part that you really don't have a calculation to justify, it's just pictures.
But sorry, before that,
Yeah.
the partition function then is just a sum over all such distinct H's, right?
Yeah, so in fact that's exactly what we are trying to fix actually. Because of course if you just work with these microscopic H variables that are in units of 1/3, you gain nothing. So you don't want to do that. What you want to imagine doing is you want to somehow imagine coarse graining these H, right? And work with some coarse grain field little h of r. And you want to be able to write down the partition function as something to do with this guy. And that's the tricky part. So let me give you some argument. And so the argument is actually just a picture.
Some sort of counting problem.
Exactly. This is a counting problem. So here's the counting statement I'm making. So I'm going to draw you a pattern and I'm going to make an observation about, sorry, let me draw it a bit better. So there's a diamond here, there's a diamond here. So there's a hexagon with 3 diamonds, and this hexagon has no diamonds. This just radiates outward like that. Okay? And now you can see how I can continue the picture. Wherever I see 2, I can put a third. And then there will be some hexagons that have no diamond on them, with 6 radiating out. So 1/3 of them will be like that, 2/3 of this will be like this. Okay? So let's look at this picture. The claim I am making is that when you look at this picture, you can, by using my construction rules for capital H, see that there is no drift in the value of capital H. If I just follow H along any direction out to infinity, it will just have a ripple. Let's say I start with 0. And what was my A side? This was my A side. So I use my rule, I'm going like this is minus 1. Okay? But now this is a B side. And I'm again going like this becomes 0. Right? So this has got some ripple, 0 minus 1/3, 0 minus 1/3. It doesn't drift. The value of H in H space is not drifting when I move out from
this particular configuration.
in this particular configuration. And if you analyze why that's happening, you can see it's because there's lots of these hexagons like this which are 3 on them, which are flippable. I can take this diamond and put it here, take this one and put it here, and take this one and put it here. And I don't need to do anything else to satisfy the diamond. Right? And it's because of the presence of these resonances or flips or allowed flips. You can see that that's why this height field only has a ripple and not a drift. Contrast it with the case where there are no, so I'm just showing you 2 extreme cases. Okay. So here's the other extreme case. Just put diamonds on one orientation only. That's a perfectly valid configuration. Okay. Now you can see again what's happening with the height field. Let's try to. So this was 0, this was A, this is minus 1/3. Did I get this right? This goes here, this goes here. So A. So start with this. This becomes minus 2/3. Right? This becomes minus 1. That's right. So if I go in this direction, I'm going to be steadily decreasing my heights. In the direction perpendicular to where the diamond is oriented, I'm just going to be steadily decreasing my heights. That's not surprising because think of your magnetic field. There is now a net flux of magnetic field cutting this plane. Right? And so the corresponding vector potential, the 2-dimensional height field, is just got a linear gradient between the situations. Right? So the statement is that lack of local rearrangements corresponds to net tilts in this height field, and lots of local rearrangements corresponds to no net. Okay? Now here's the coarse graining step that's ill-defined. You no longer keep track of every microscopic configuration. You don't distinguish configurations if they're not going to have any effect on the length scale you're looking at, which is some coarse graining length scale. Right? So in effect, your partition function is not now the sum over all microstates, but the sum over states that can lead to distinguishable outcomes on this length scale, which is some coarse graining length scale. Right? Now, therefore, you should then ask how many such states there are that lead to no distinguishable outcomes at some length scale. Right? And the answer is if there's lots of local rearrangements, there's exponentially many of them. If there's, so then you say that there is a weight factor. So there's an action now, which is basically because net magnetic field, so you constrain the magnetic field also. Having a net magnetic field in a configuration, net flux, is going to lead to very few local rearrangements, exponential suppression of Boltzmann weight.
So, again, I thought you were going to say something like this. That suppose now I take an A cross A box and I define some sort of average H.
Yes, that's what I'm going to do. Yeah.
And then you count how many configurations correspond to that.
That's exactly what I'm saying.
Okay.
But I'm saying it slightly differently. But yeah, that's what I'm doing.
Yeah.
And so distinguishing the case where you have an exponentially large number from where you have
Right. And so I'm saying this factor goes into the exponential. So when Z, very schematically, Z is some dP each with a minus index. Okay. This is some stiffness. And of course, P has to obey my constraint, and so then this is just gradient.
So your average H is what? Is it H divided by number of units or just sum of H's?
It's the mean value of H in a region. Yeah.
Okay, it's a mean value.
Yeah. Mean value of H in a region.
And so, forgetting about the derivation, the claim is that the number of states scales like.
So the claim is that if you take the partition function, some coefficient for certain purposes, this is good enough.
The price you pay, in a sense, compared to some fiducial choice is.
But this is just a counting question.
This is a counting question, and in fact, I don't know how to make this rigorous, but this result with suitable caveats and meanings attached to it is actually proved by this mathematician.
Okay, so it's a true statement.
I would claim it was a true statement before you proved it. It got proved when you proved it. Okunkov and Kenyan.
And he can calculate the number behind it?
No, I don't think so. Well, actually he can. I'll tell you why. Because all this work I'm doing is in the end reproducing an exact solution where I have to calculate some determinant. Okay. And if you have sufficient analytic control over some asymptotic properties of some determinant, you could get everything you wanted. But you know the coefficient. We know the coefficient. Yeah, including the coefficient.
And
the way I know it is I work backwards and I fix.
that's fine. But you have an analytic expression.
That's
I mean, not a
That's
plus 0.01.
That's right. No, there's a number.
That's
There's a number.
We just want to say, you determined, you mean, for example, someone has worked out the partition function for your diamond model.
That's
what you
That's writable as a determinant of some big matrix. And what these people did, I think, is they did some very hard real analysis or whatever of that problem and established that answers you get from that in certain scaling limits that they can define rigorously are answers you get
with
from
this and with some coefficient.
So this was all only counting because you assign weight 1 to everybody.
I
And now if you did
I lost that weight one because I agreed not to distinguish configuration.
Yeah, so that I understand.
Yeah.
So but if you wanted to refine it, it would be some higher dimensional operator.
If I wanted to
or
refine it in the sense
maybe
I
that
wanted to
now it's
weight.
actually it's not weight 1. If you
So that corresponds to interactions in the diamond model.
so
Microscopic.
is it representative in this theory?
It is actually. So that's a little bit more work, but in certain cases the interactions are of a form where one can argue that they lead to a certain cosine term that adds on to this. And if that cosine term is irrelevant, all it does is it changes the value of the coefficient. So the coefficient can be made to flow.
The question you're asking is if you relax this dimer constraint.
No, he's asking if all microscopic dimer configurations don't have equal weight.
In the original theory.
In the original, I see.
So you can then.
There was an energy in
Yeah.
dimers.
So we've looked at, many people have looked at that, including us, and the answer is, I think that at least in some simple cases, like if you have an interaction that favors flippable hexagons, favors hexagons like this. So apart from weight 1, there's a weight which is just some number to the power number of flippable hexagons. Right? So in the energy, you give a weight to it, you give a negative energy to every flippable configuration.
Wait, but isn't that an important question here about whether there is an interaction term that is the wrong wavelength limit breaks the rotation limit?
Yeah, so so breaks the rotation limit.
But you've got an effectively two-dimensional rotational invariant.
Yes. Yes.
And it's more conceivable anyway that Gautam's energy functional,
Yeah.
even in the long distance limit will break that.
So no, then it's different.
Yeah.
Then it's different. I'm imagining I'm imagining interactions that preserve triangular lattice.
And you have a proof that any such interaction will give you operators that will, in long distance limit, be because all those will be irrelevant.
Yeah. Well, no, they can be relevant also. If they are relevant, you will actually lose this entire phenomenology, and the dimer model will order.
What I was saying was that anything that preserved the triangular symmetry but not the rotational invariant.
Yeah. So all my things always preserve only triangular symmetry and not rotational.
But are there relevant operators that preserve triangular symmetry but not rotational invariance?
Oh yeah. I mean, I can write cosines down, which become relevant. That depends on the sign of the coefficient. I mean, not the sign, the magnitude of the coefficient.
But those will give you gaps.
Yeah, those. So you'll have transition.
I see.
I was just trying to think about that. At least if I do naive dimensional counting, you might think if you could write down a term with one, let's say it's quadratic in H for some reason.
Yeah.
If there was a term you could write down with one derivative,
Yeah.
which you can't if you have rotational invariance.
That's
But
right.
since you
So
have
one derivative. So one derivative corresponds to fugacity of differences. So you could say that dimers on one orientation of rings have a different weight from dimers on another orientation of rings. That doesn't come out of this JOD perturbation theory that I started with, but it's a perfectly valid way to define dimer models and study the counting problem, and it's been done. And then that corresponds to linear derivative terms in this, and that's just like tilting this. Grad h square minus alpha grad h dot some direction, right? And then there is just a linear instability.
Correct.
That's been studied. In fact, I think Muskan will know this better than me. But if you say there's fugacity 1, 1 and z is bigger than 1, then what happens is you go from this phase, which is power law, eventually to phase which is just this. Everything just points. It's a fluctuation free phase. And there's a very funny classical phase transition in this counting problem as a function of z, which you can model by putting a minus grad h dot some direction.
I see, it's just
Yeah.
grad h dot.
Yeah.
I see.
Yeah.
So, but I was just thinking naively, suppose you started writing down operators,
Mhm.
now allowing for preferred vectors,
Right.
So, now what else could you write down? I was thinking maybe there's a reason why it has to be quadratic. and
Right.
it's
No,
not-
but
maybe
in
not
this
even
case,
that.
not even. Yeah.
So then there is a bunch of terms.
That's
you could
right.
write
That's
down,
right. So those I've not thought about very hard because they don't seem to arise in this JOD perturbation theory, but they have been studied in the combinatorics literature. Like this transition I just described is, I think, called the Kosterlitz transition. So if you want to look up one name, it's a funny transition because if you think of it as a thermodynamic transition and use our usual classification of transitions, it somehow got features of first order behavior as well as second order behavior. So it's on one side it's completely fluctuation free. So there's a way of thinking about it which is special to the Kosterlitz transition.
So the kind of terms you're thinking about are changing the coefficient of del x square and del y square.
But no, I was thinking of
That
terms
would
which
be
would be allowed because you're breaking rotational invariance.
Exactly. So,
Exactly. But yeah, exactly.
So I was wondering, is it clear that there's something that preserves the triangular symmetry? You can write those things.
Yeah. In fact, they are important.
It wasn't clear to me.
So for example, you can write things like this. Grad 1h, grad 2h, grad 3h,
That's cubic.
in the three directions, right? And if you have these tilt things, then cubic is allowed. So you can have terms like this. If you are now allowing tilts.
So this is sorry.
Yeah, that's right. But terms of this kind, where you have derivatives in the three triangular lattice directions, this will be important.
Sandeep was asking, can you treat the kinetic term in a way that preserves triangular symmetry?
No, I don't think
What
so.
I was asking was,
No.
because ultimately you're going to roughly say that we are at a Gaussian fixed
No,
point.
you can't do
at a
that.
free fixed point.
Yeah.
So let's try to do
Yeah.
a self-consistent
No, so
analysis.
grad h square you can't change.
No, but you can have single derivatives.
Yeah.
Because you have vectors.
Yeah.
So for example, you wrote down grad h dot e, but you
Yeah.
could also have you could have h grad h dot e.
Yeah.
And so on.
Yeah. So if you destroy the triangular symmetry by putting in directionality in the fugacities, yes.
No, but if you just preserve the triangular symmetry, then you have it doesn't
Then you can't do
You
it.
try something like grad 1, grad 2, plus grad 2, grad 3.
Maybe with
grad
linear derivatives.
That's right.
He's already allowing.
But a linear derivative is like a total derivative.
No, I mean your fugacity term was not a. Was
So
it
you want
Fugacity
h
term
del
produces a
h.
91.
You want h del h.
something like that? Yeah.
But you have to be careful that that's not del of h.
I know. Okay, now why was grad h dot e not a total derivative?
Yeah, but it says there's a tilt. I mean, it's not. It just says that you like configurations with a net tilt. That's all.
So maybe any power does something similar. I was just wondering. I mean, maybe you can make your argument just precise like this, right? That
No, so the real difficulty I think is not saying there's nothing other than grad h square at this level.
Okay.
It's actually ruling out cosines and things like that would gap the system, right? Ruling out cosines that would gap the
E to the
system.
power I.
Yeah.
those
I think those are those who I don't see how you can rule them out by pure thought. That's the
But then there's a lot of knowledge about that, right? You
Huh?
take the Gaussian theory.
that knowledge I'm using to the hill. But I'm saying what's the bare value of it to still be relevant? It could be large enough that it's relevant. Right? You only know about perturbative things around the Gaussian fixed point. I'm saying we don't know enough about the thing to know what's the coefficient of the cosine and whether it falls in the realm of that perturbative thing where it flows to zero.
How are your dimer correlations
I'll come to that.
But H is not a periodic.
H is periodic. H. So you did not miss it because I did not say it in this language. Let me say it. So now we have to be very careful about symmetries of the theory, right? So you have to imagine. So the argument is a little subtle. So I won't do the whole thing. Drawing pictures like that is a bit beyond me. But imagine you have some box in which there is a honeycomb lattice, and you have a configuration of diagonals, right? And it has some weight. Now imagine shifting the whole configuration forward by weight. Okay. So the local region shifts to here. Just translate. Okay. Now in that local region, it's the same configuration, so the number of local rearrangements is the same. So our coarse grained weight should not change. And all that's happened is that you had some reference point 0 where the height was 0. The place where your box is has moved relative to that reference point. Okay? And you can show by using these microscopic rules and making an argument that this symmetry, which is just the symmetry that shifted configurations have the same local contribution to the entropy, right? Gives you H going to H plus 1 as a symmetry of the coarse grained.
Is it literally plus 1?
Literally plus 1. And that literally plus 1 simply comes from this fact that if you have 3 empty links, you get a minus 1 when you go out. That's all it comes from.
So this is a local statement.
This is a local statement. No, sorry, what do you mean local statement?
At its
Every H of R moving to every H of R plus 1, it's a global statement. It's a global statement. Okay, so there is a global shift symmetry, which means your boson is periodic. Okay, with period 1. That comes just from saying that configurations shifted by 1 unit must have the same number of rearrangements, but they have shifted by 1 unit relative to some reference point from which you measured your heights, and that gives you a shift.
So if you do these shifts, you don't change the time.
You don't change exactly. Right? You don't change the rearrangements.
The time observation.
You don't change the rearrangements, and so you don't change the weight in the Boltzmann weight, and that's what your action is, whose symmetries you're trying to work out.
Maybe it just follows from the fact that D was defined through epsilon mu H.
So it's a little bit more. Sorry, it's a little bit more.
I would have
It's
said
a little bit more. Yeah, there's a little bit more. Okay, so that's one symmetry.
The difference between compact and non-compact human theory usually is only clear if you have matter. I mean, I don't know. Okay, I'm with somehow I didn't.
No, so here it's just translationally.
Yeah, it's just further from the fact that you're getting your numbers from H with a difference operator.
That's right. So no, it's not just that. It's actually it goes back to what's the weight of a, how many microstates are there in this box.
Wait, sorry, we had an algorithm telling us what NX was in terms of H.
That's correct.
Now I just want to see whether NX changes.
NX doesn't change.
So then that's over, right?
No, what is NX? NX is
It's the number of diamonds. Your original configuration.
B.
That's correct. That's correct. That's correct. I agree.
Occupation. You had these links.
No, but
either occupied or not.
I think that is correct. But it's also important for other purposes. So I want to state this like this: that translating. So there's translation symmetry in the original problem. You can ask how that is implemented in this theory. The claim is it's implemented like this.
But just logically, the fact that NX doesn't change means that this is a
That's correct.
This is a redundant.
But this is actually also translation symmetry in the Newton.
The fact that B was curl of H would allow H to shift by any constant. So you're using more than that.
No, any constant but one. One comes from
the fact that
translation.
it's one and not any constant. That is
It has to be
more than B is
So the microscopic guys, when they change by one, that's implementing
That
translation.
may be, but this shift by any constant is a redundancy of this one.
In the
but
Kosterlitz-Thouless
this
yes.
is more than that. See,
This is more than
this
that.
is more than
You
that.
need the
That's
number one.
trivial.
No, but why then what I'm not understanding is why can't we shift by 1/3 and claim that this is
No,
a
you-
one
you
third?
can't.
That's a non-trivial part of the
That's
game. I
not-
have not understood.
Why not?
So
it is
you-
true, right? If you shift
No,
by 1/3,
no,
you get the same answer.
So the cosines change.
No, I haven't understood this. You've not changed the NXs.
Yes.
I thought what you
So
wanted.
let me say it this way.
This is
Okay,
exactly
so
what I'm
actual,
saying about
let's write that. Let's write this. No, let's write this. So the action is this. Okay. Plus some coefficient lambda 3 cos 6 by h. This is the action actually. Whenever I write grad h square, that's actually shorthand for this theory where lambda 3 happens to be irrelevant. But it's dangerously irrelevant. It actually controls answers as it flows to zero.
So, but I'm asking a much more basic question. For So very well, you know what the final
So
answer.
no. So now if I shift by any constant, this goes off.
I understand, but this is at the end of some process.
Yeah.
I'm starting at the beginning.
Yes.
You actually wanted to count the number of nx's.
I wanted to count the number of configurations.
Number of which was nx's, which were 1 or 0.
Yes.
Then you switch to a problem of labeling those nx's by h's.
That's correct.
So if you've got two different h's,
So, wait,
but you write to the same nx's,
that's
they by
capital
definition
H.
the same.
Hang on. That's capital H. Right? I'm no longer working with capital H.
So this is some smeared thing.
This is some smeared
So
thing.
but
The important point is that the smeared thing has this shift symmetry.
Okay.
One exactly being one.
Okay, so to understand this, I would have to understand what you mean by the smearing property.
Well, so the smearing properly I can only explain to this extent. Make a box and count all local rearrangements, add up all their weights.
It could be there's a factor of 3 in your that your average, your age is 3 times the average of your age.
No, so you can fix its normalization whichever way you like. If you fix the normalization one way so that the term that appears here is cosine 6 pi,
I understand.
then the shift symmetry is h going to x.
It's somehow that the periodicity of the average is not the average, is not the periodicity
That's
of the
correct.
period.
That's exactly
That's the
right.
problem.
So
Gives rise to the cos 6 pi h.
we'll come to that. Okay, we'll come to that. Well, the basic answer is it's allowed by symmetry. And I can give you its interpretation in terms of these interactions that Dr. was asking. This I can interpret actually as the 3-dimer interaction coefficient that likes to make flippable things.
So for example, cos 2 pi h is not allowed.
Cos 2 pi h is not allowed for a reason which we have not yet come to. Let me come to that. Right now I would have allowed cos 2 pi h. Right?
No, because the argument is a little bit is that you have a certain set of interaction terms which are allowed,
Yeah.
and then you read off in a sense the periodicity.
That's right. So far I have not told you anything beyond this, and at this level cos 2 pi h would be allowed. But there's another symmetry which is rotations about a point. Right? So you rotate the whole configuration. So if you implement rotational symmetry in this theory and again carefully think about what it means to force grain in a box, that corresponds to h going to I think h plus 1/3.
That's great.
Yeah.
Okay, go on.
Yeah. And then there is a final symmetry which is a reflection which corresponds to h going to minus h. Okay, so these are the 3 symmetries by just asking how does this coarse-grained little h implement the microscopic symmetries of the triangular lattice problem you started with. Okay. You learn that h going to h plus 1 everywhere on the lattice, h going to h plus 1/3 everywhere on the lattice, and h going to minus h everywhere on the lattice are symmetries.
But isn't h going to h plus 1/3?
Is contained in, yeah.
Contains
But we
the
consider this
variability
sort of more basic because it comes just from translations.
Can you say that again, please? I missed that part. How h goes to h plus 1 is translation.
Right. So the statement is you started with some origin where the height was always 0. Okay. And now you are asking what's the contribution of a block. I mean, how many microstates this block has. The statement is whether the block was here or shifted by 1. The number of microstates it contributes to the partition sum doesn't change.
Yes.
But its mean value of h averaged over those microstates in the box changes by 1.
So why does it change by 1?
So it changes by 1 because, let me draw this. Okay, so let me draw a picture that's a bit better on the square lattice. It's drawing pictures, that's the difficult thing. So let's say I'm doing the square lattice diamond problem. Everything else is the same. Now the 1/3 becomes a 1/4. Okay, and this is the place always where I started with the origin. And I had some dimer configuration which was, let's say, like that, like that, like that, like that. Let's just take this. Then I start, and this is my box whose average I'm going to work out. Now, to go from this 0 to here, I would go here and then I would cross like that. Right? And then this would be some height. And then all other heights are determined from this height. Right? Now you shift by 1. You went from a filled link to an empty link. So instead of going up by 3/4, you went down by 1/4. So that's a 1. Same thing happens on the honeycomb, but I find it harder to draw.
Instead of going up by 1/4,
Going down by 1/4, you went up by 3/4. you know, this 2/3, 1/3, 2/3 minus 1/3 becomes plus 3/4 minus 1/4, right? So your microscopic rule tells you that the microscopic constructions of the heights that you are coarse grained tells you that translations is implemented this way.
Namely, if what you're blocking over you change by one fundamental.
Just move the whole thing.
One fundamental.
There's a little subtlety here. When you move the whole thing, you have to kind of imagine that if things were on the boundary, you will put them there. You know, you will shift. There's a little subtlety.
It seems to me that clearly from this point of view, what you're saying is that your coarse grained edge is the average of your edges.
Average in the sense that I make up all configurations I can inside there.
I'm saying there's no factor of 2 or 3 in
No.
edge, because you're shifting by one.
Yeah.
You're shifting a little bit by one.
Yeah.
Big by
Yeah.
coarse grained. But somehow you're getting that the periodicity is different. The fine grained periodicity of H's was 1/3.
Yeah, but that's also a symmetry. So if you implement rotations, you get that.
But we're not. There was some redundancy and there was a symmetry.
Right. So this is a redundancy.
Right.
This is the point. So therefore, if you want to, in your language, ask what's the compactification radius, that I would say is 1 because that's just a redundancy.
So, but the fine grained redundancy was 1/3.
Fine grained redundancy was 1.
That
Coarse grained redundancy is 1.
And that is the key point.
That is the key point.
That in the average, you
That's
can
right.
change this redundancy
So,
from 1 to
redundancy is 1, but rotational symmetry, if it exists, will still allow you to claim that your action must be symmetric, h going to h plus 1.
And the 1/3 is the redundancy or symmetry?
It's a symmetry, triangular lattice.
Okay.
Symmetries of the triangle. It's one rotation, 6-fold rotation.
Well, it's some large gauge transformation, small gauge transformation.
Oh, okay, I don't know.
Yeah.
It's something
So-
subtle. It's something. This kind of thing is very subtle.
Yeah.
Maybe
So-
you introduce charge matter in some way.
No, but
No, no,
it's
that's
not that.
okay. Fine.
So anyway, this is the story so far.
Okay.
The action is this. Right? Partition some images with some coarse grained things, which I am taking Gaussian, but you should remember that allowed are terms like cosine 6 by h and higher ones. They are allowed because h going to minus h going to h plus 1/3 are symmetry. H going to h plus 1 is a redundancy. So you can't make that tells me what operators I can pay, right? So this tells me the symmetry is needed to say what's the coefficient. But I could always make an operator which is equal to I pi h. That's not a problem. If I put something in. Right? Okay. So that's good. Now let's talk of spins. Yeah.
The fine grained gauge didn't have a Hamiltonian.
Hmm?
Yeah,
It
the
had
fine
energy.
grained gauge didn't have a Hamiltonian, right?
Fine grained.
Like the.
It had energy which was one for all configurations.
Exactly.
That's right.
Basically,
Now I've done some coarse graining. So now in the language of H, different H configurations have different energies.
Yeah.
Right.
So this del H squared you pointed out, you argued that okay, del H squared count the number of those three dimers in one
Right.
second.
So if there's lots of local rearrangements possible, this has a very low value, and if there are no local rearrangements possible, there's a net tip.
Yeah. So what are the number terms? What is 6 by h2?
Coming. It's actually capturing interactions of the form. So if there's a 3-body interaction that likes this to happen, its coefficient will be this.
It's a complicated counting problem
Yeah.
for which you're doing some asymptotics.
So in fact, we know quite well that this interaction changes this coefficient. That we know. Okay. In fact, you can make this interaction stronger and stronger and stronger, and change this coefficient until it goes out of that perturbative irrelevant basin and it just gets gapped, and you get an ordered state.
But what is the value of the coefficient CK?
Which coefficient?
The coefficient of cos 6 by h in the.
Oh, so that's tunable by this interaction is what I'm saying. Without this interaction, it has some value which is irrelevant. I don't know the number. I just know that it's irrelevant, and that also I know after the fact. I mean, this works when it works, right? The gradient square, like all things. You know, when I flow into that Gaussian theory, I can make calculations and check. Right?
Wait, but just in the original diagram, the one
Yeah.
which was just the
Yeah.
triangles
Yeah,
itself,
yeah, yeah.
you could imagine just doing a counting problem. If you define your coarse grained H properly, you could imagine doing a counting problem, doing some asymptotics of that, and
Yes.
deriving this.
Oh yeah. So that's exactly what Stephenson did and people did, right? So we are just trying to so we are trying to get that answer in a more coarse-grained way.
Yeah.
Right? That's what we are trying to do, and the hope is when we do that, we can then do things that that counting problem couldn't do. Because I can put in interactions, I can see what happens, so on and so on.
But even just making your way of thinking precise, one could do in a counting group, right?
Right. One could do well in accounting. So the way it was done by Okurkov, I couldn't read the paper, but I could see what they start with. They start actually with the exact Hopfian expression for dimer correlators and for the partition function, and then they do some heavy-duty analysis for those expressions.
Can we do some sort of algorithm?
Yeah. So that I haven't seen implemented. Right. So
I'll step by step, basically.
so that I haven't seen being implemented.
Even on the exact.
Is on the exact. Yeah. So that I haven't seen being implemented. Do you know any attempts to do real space RG, for example?
There's no idea.
No.
They might well be. It's
Well,
just very
Shaunak has some RG these days he's playing with, which seems to work quite well, right? This tensor network renormalization. At the level of computing partition functions and free energies, that's
It's not analysis.
It's not analytics. You're basically implementing it.
And then actually it looks like it's like 8
What's the question?
It's like interface.
So it's, you see at the end the dimers is if you think in a
There is a
triangle, it's the interface.
Absolutely,
And
there
you're
is a
looking at
connection.
equilibrium problem.
Yeah. So
Which is just Edwards-Wilkinson. And
Yeah,
the action gradient is the Edwards-Wilkinson.
sure.
action.
But there's an even better connection. So triangular lattice triangular lattice antiferromagnet configurations have a mapping to solid and solid on solid
So
quantities.
SOS model also leads to
And there's beautiful work by Lord and I think it's called triangular icing antiferromagnet and S crystal shapes or something. One.
And an umlaut.
Yeah.
So the reason I was saying
Yeah.
that in the interface problem, you can show that in the action all the other terms are irrelevant in this equilibrium problem.
So you
the
can
gradient-
show means what?
So
I mean, I can also say that cosine is irrelevant for certain values of this coefficient.
it's irrelevant
But you
in
need
the
to know
way
the
that one writes down Edwards-Wilkinson and
Yeah.
busy type and show that any higher order derivatives.
No, sure. So that's the kind of argument we are exploiting when we work with gradients. Okay. That's exactly the argument. That's correct. Okay. So now strings. So that this was supposed to be a small okay. No, but this is good. So okay, what's the other thing I wanted? Let me skip the connection to odd icing. That's a more. Let me just say it in one sentence. The point is the way I'm doing it here. It somehow has a flavor of something you want, right? I'm writing magnetic field and everything, right? But that's totally fake at some level, in the sense that if you take the triangular lattice icing antiferromagnet and look at its configuration space, there's a one map, it's a duality map between that configuration space and the odd icing gauge theory on the honeycomb lattice, right? So because you see, every triangle can have one frustrated bond. Or, so let me draw frustrated bonds like this. One frustrated bond or three. Right? And this center side, which is the honeycomb side, right? You can now define a dual icing gauge theory where the
I'm sorry. If the three
All up.
are either plus or minus.
all up has three frustrated.
Sorry.
Right? So it's 1 or 3. It's not 0 or 2.
Correct.
Right? And if you run the usual Hamiltonian formulation of duality for icing gauge theories, you will see that on the dual honeycomb lattice, you actually have an icing gauge theory where your product over the tau x's, that thing is actually minus 1, not plus 1. The constraint, which is product of tau x's, is plus 1 usually, is now minus 1. Okay, and the minus 1 has to do with the fact that this is an odd number, 3 or 1. This is just standard Coco review article or something. So writing it like this is a bit fake, and sure enough, there isn't really a quantum mechanical theory where in 2 plus 1 dimensions I'll have a U1 kind of description, right? Because there's no defined case of it. But for our purposes, just for doing this much, it's perfectly good to do this, right? So
But I mean, you are in two space.
right, so I'm not, right now I don't have the plus 1 and I'm not talking of quantum mechanics, I'm just doing the counting problem, so it's okay. But I just want to caution you that if you think I can now introduce quantum mechanics by adding terms that are like b square plus type derivatives, that's not good.
Just one question, sir.
Yeah.
These three triple frustrated is not there in your model.
Right, is it icing model. It's not there in the dimer subspace, which is the zero energy subspace. But I'm just making the point that the microscopic dimer model, microscopic icing model with frustration, right? The configuration space is exactly the configuration space of icing gauge theory on the honeycomb lattice. So in fact, the statement which is in the square lattice version of the statement is in Kosterlitz-Thouless, right? That if you take the theory which is minus some coefficient tau z, tau z, tau z, so 6 of them. This is the plug. So six of them, right? Minus gamma tau x. This is the icing gauge theory, right? So honeycomb lattice version of the standard solution. This is exactly dual to the triangular lattice icing antiferromagnet with gamma and j with the j. In other words,
This is allowing also not minimum energy configurations. That's why.
just basically gamma. Sorry.
Because earlier we were working only for
Yeah.
subsets.
So, but just to complete, I think this is exactly the same as saying gamma sum over I j sigma z minus j sigma x. So just transverse field and exchange get interchange. So this is exactly right. So therefore you should be careful about thinking of magnetic field. Okay. So now strings. So now let me try to draw. So first statement is the simple one. The fine grained statement. The fine grained. Both are actually relatively fine grained statements because for operators I can never forget the fact that I'm on the triangular lattice. But the first statement is that every frustrated bond from here to here corresponds to a dimer. And so frustrated bond means this is the same as this. That means there was no spin flip. Right? In terms of heights, what happened? Remember the height jumps by 2/3, plus or minus depending on which way you're going, whenever you cross a dimer. And only by 1/3 plus or minus when you don't cross a dimer. Right?
Roughly.
The 3h. This will
Yeah.
just give you a 3h. Yeah. So if I looked at the change in 3h, if I follow any path from the origin to my site of interest xy, right? 3h is going to jump by an odd amount only if there is a spin flip, right? So the number of spin flips I encounter is the number of times 3h jumps by an odd amount.
Odd integer.
Odd integer, not even integer.
Correct.
Right? So therefore sigma of xy is going to be sigma of 0, 0, spin at the origin, into e to the 3I pi h. So 3h, if 3h, the net jumps were odd, spin has flipped, otherwise it's not. So I'll get a
Minus 1 to the cross 3.
minus 1 to the right. So there is certainly this way of writing the spin down. But the right way to think is that this is some microscopic operator, and so this is always one. This is a microscopic operator, and this is one piece of that operator in the effective case. It's not the only one. Now I'll show you that there's another way of thinking where I get a different expression, and that's the other piece. Okay. This piece you can see is going to be subdominant if there's any pieces with numbers smaller than 3. Right? So in fact it will turn out that this gives you the 9 halves. Right? And now to get the half, I need something which is the I pi h. Right? So that logic is a little more involved and uses the triangular lattice a little bit better, more in fact. So you imagine going like this. So if I want to go from 0, 0 to any point xy, the way I will do it is I'll go like this to some place which I will call x comma 0, and then like that, okay, to wherever I need to, and then this is x comma y, like that, okay. Okay, so now again the same point as I keep going, right? How does the height change, you ask, right? So remember that NL minus 1/3, right, is h. Sorry, NL minus 1/3 is delta h. The change in NL minus 1/3 is the change in h.
So every path should give us the same change.
Right. So I'm just, that of course we know is guaranteed because I'm working on the dimer subspace.
Yeah.
So I'm free to choose gives me a formula that looks different.
But that will always give you e to the power 3
No.
by h.
I gave you one logic which didn't care about what path I took and always gave me this piece. So here's another way which seems to give a different answer, and you might wonder which of them is wrong. The point is, these are just two heuristic arguments that tell you that the full operator is some coefficient times this plus some other coefficient times the piece I'm going to derive.
Wait, in the microscopic model,
Yeah.
this was just exact or not?
I think so.
Yes, in the mic, that's correct. If you had capital H, it was exact. But now I don't have I'm going to write this with little h.
Okay, but firstly in the microscopic
Yeah,
model,
yeah, that's
you're not
this
going
is
to get a
exact
separate,
treatment.
you're not going to get a different formula from this in the microscopic model.
Let's see what I'm going to say.
Okay.
Okay. So I go like this, and then I go like that.
Okay.
So NL minus 1/3 is delta H. Agree? What NL minus 1/3 was delta H. And this is basically this NL minus 1/3 is this delta H.
Yes.
Agree? So if I want to, and the height here is set at 0. So if I want a height here, I will want to add up these delta H's. Right? So I need to add up these NL minus 1/3. Right? All the bonds I cross. Yeah, there. Right? And so you can see that the number I cross will be at x. So okay. So the number of n is, and now 1 minus NL, right, is the number of spin groups. So I want to finally decide if this fellow was pointing in the same direction as that fellow or not. Right?
Exactly.
That
That is
I,
what a 1 or a minus 1.
that I can get by also saying that I will take 1 minus NL and add it up. Right? 1 minus NL and add it up and do e to the I pi that times that.
Yes.
Right? So if I do 1 minus NL and add it up and put e to the I pi in front of it,
Yes.
what am I going to get? I'm going to get a 4/3 x 4/3 x plus h at that place. And this is going to get multiplied by e I pi. That comes up to here. I just put 1 or minus 1, exactly the way Kedar wanted, but I did it this way. Now I'm going to go up and do the same thing. And now what's going to happen is the h, instead of being the h here, is going to become the h xy, but I'm also going to get a piece 4/3 y.
Where did the 4/3 come from? Sorry.
1 minus 1. Sorry.
I see 1 minus
1 minus
1 minus NL,
Yeah.
where NL is
Yeah, well,
delta H
actually,
plus 1
Sorry,
third.
it's different. So it's different.
Okay, so in some counting, I
Yeah.
got it.
It's the same as complex. So you see, there's another way of doing the same plus 1 or minus 1 factor, which gives me a different looking formula, right? And it actually gives me a e to the I pi h.
So I need to think harder to understand the but it seems to me that there is a unique answer about when you've got two spins, either they parallel or they are.
That's right.
H's.
I'm saying both of these give the same answer, always. This formula and this formula. For the, if instead of little h being any coarse-grained field, I stuck in the microscopic values of the fields and the points, this formula will identically give you the same sign as this formula.
And that follows because H's were constrained according
In a
to your
particular
del
way.
dot J.
Exactly. In a particular way.
That constraint ensures these are the same.
So I'm writing the same sign plus 1 or minus 1 in two different ways.
And
But now in the coarse-grained theory,
obviously.
by construction.
Yeah.
But in the coarse-grained theory, they could give me different answers.
Yes. So you don't know how to constrain it.
So therefore I'm going to say that the real coarse-grained operator has a piece corresponding to this and a piece corresponding to that.
Okay, but how is it there's a third way of doing it?
I don't. This is enough for me to get Stephen's. Okay. I think this is it basically. I mean, once I produce it to the I pi h, I know all powers of it are anyway there. It's not a big problem. All odd powers.
You omitted the thing in the middle, e to the power I2 by. Oh,
No, that's very crucial.
That's twice
In fact, the reason I like this argument is it gives everything right.
Oh, I see.
But it's a bit of a fraud, of course, because I've done no real work and I've got the answer. Right? So the claim is sigma of x bar. So what's that?
Answer analysis. You
Answer
know what you are getting.
So the some coefficient plus, and of course all order powers of this are there. Anyway, right? Subdominant pieces would be there in the answer. Right? So, but anyway, so there's some coefficient here, some coefficient. Now what it just now you understand why exactly we got those powers that we did. Right? free bosons, and you have to multiply the basic power by 9 to get the next power.
The non-oscillating terms sort of suggests ferromagnetic of some sort. Right?
We'll come to that. So that's very important.
Meaning of that.
I'll come to that.
Yeah.
I'll come to that. Let me just. That's actually very crucially related to the real talk. So I've not got to my talk.
What is Q?
This wave vector, 2 pi by 3 to pi by 3.
Yeah.
So Q dot R is 2 pi x by 3 plus 2 pi by 3.
It's a basic lattice.
Yeah.
Kedar, can I ask you something? Aren't you saying basically this frustrated system is a scale invariant theory?
Right. So the averages in the ground state ensemble give power laws. Yes. And in fact has a representation in terms of the free boson, and then calculating physical quantities involves calculating these correlators.
But just in terms of thermodynamics, is that correct? That if I computed just basic thermodynamics, it's a scale invariant system.
Are you asking, for example, if I write finite size effects, will they also be powers and not exponentials?
Yeah,
Yes.
so
That's right.
That's all correct.
That's correct.
Okay. So
That's
that's all borne out.
So in
by
terms
the
of this
actual-
sort of determinant calculation we do, the matrix whose determinant we calculate is gapless.
Yeah, yes, okay. Okay, so that part is all true.
Yeah.
So you say, all right, it's a scale invariant system, but just the operator, the microscopic operator, because what Stephenson computed when he computed 2-point signal, he really literally took the microscopic
He
scale,
in
right?
fact had to, so the determinant is the answer of the partition function, and then there is a more complicated object you have to compute to calculate correlation. And he computed that.
Right. But is the microscopic spin correlator?
That's right.
You're saying that maps
That's
in this component.
That maps to this. So I'm saying computing that the way Stephenson did is equivalent to computing with f equal to Kedar h square with the specific coefficient that I don't know. Right now, nothing I've said knows that coefficient, but I know that this is the operator identification.
And this one can see from symmetry by the rotation shifting h by 1/3.
Yes.
That gives you a phase which will be compensated by rotating by
That's
2.
right. That's it.
You want to see that this operator preserves the invariances of the original run.
Yeah.
So Kedar told us that rotating shifts little h by 1/3. So that e to the power I pi h picks up a phase,
But that gets
compensated.
Yes, yes.
Exactly.
So if you had to
So
get
this is a good
power
operator.
different from
Yeah.
3,
So this is a good operator.
and maybe you could rule out 2 pi IH, I mean just as an example.
But that's
Because
ruled out, I think,
there is
because
no Q.
I think what happens is all odd powers of this basic object are like even powers will have the wrong symmetry.
So,
Under spin plane,
so I mean,
right?
I see. So,
This is just, I think of this just as the cube of that. And it's
no,
not
but I was just thinking, suppose we didn't want to do answer.
Yeah.
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 I mean, you could say, well, what more could you add? Perhaps we can say you can't add fractional powers e to the I pi h over something.
Right, so we have to respect the following three things anyway. H going to h plus 1/3, h going to minus h, and h going to h plus 1, which is subsumed with that, but has the different status in my mind, it's sort of the redundancy.
Okay, so you want to preserve all this, but the way you're preserving it is that the operator involving h by itself doesn't preserve it,
Then I
but
might-
you add compensating things. So you might, I mean, this is probably obvious to you, but someone might say, oh, how about e to the I pi h over some
Yes.
number, but there's probably no compensating operator made out of R. I'm asking.
What if I take the square root of that whole thing?
Square root is one thing.
Yeah. Phases will stay cancelled.
So just
Or
one
not.
2 everywhere.
But is there, so that's exactly what I was getting at. Is there a reason why some integer lattice shift, I mean, just Q, can you constrain the Q dot R kind of things you get?
Hang on. So if you take square
It will
root,
not cancel. Make it both because there's
so
some
Q is a very special wave vector because its complex conjugate is itself.
So you're saying if I take my
Yeah.
two phases will not.
Yeah.
Okay.
I think h going to minus h will be the problem. H going to minus h will be the problem because 2 by 2 is not the complex conjugate. e to the I q by 2 is not.
I see.
H going to minus h.
I mean, what I was thinking was that the higher powers of H will become irrelevant.
Yeah. So
Beyond the
these
point
always
you don't-
the question is, do you have anything lower?
Yeah, you have anything
The point
lower.
is h going to minus h is also a symmetry.
Okay. So I mean, if you could show, I can't do
Yeah.
that lower powers are ruled out by your symmetries, then you have a pretty good.
I think so.
You you're
think
pretty good to just effective field theory.
Yeah,
Right? Saying, okay, we don't know, but
That's right.
just the symmetries say it's a combination of both.
That's right.
That becomes
Yeah, so the reason I guess I've not invested enough effort in it is because after doing all that, I would still need to show that it flows to the Gaussian point, and that's still answer analysis.
So, but then it's a sort of self-consistent.
Yeah. So I think that at that level it's true because these are very constraining.
And with all the finite size scaling and so on, you could probably check that it's a Gaussian fixed point. Very well.
No, in fact, knowing the answer, we can check, right?
Yeah.
We have to know the answer.
No, that's fine. That's fine. I mean, nobody can predict.
Exactly.
No, that's a very tall order. I mean, anyway, in effective field.
No, but that's what apparently. Well, okay. So I don't know whether this mathematician's work counts as actually knowing without knowing the answer because they don't actually work out the value of the determinant the way the Stephenson's calculation does. But they use the fact that it's a determinant and then prove statements that there is some free field theory that defines it. So that might be the closest that comes to not doing answer verification. Because although they write down the determinant, they don't use it to get the answer. They use it to define scaling features.
That's it.
Right?
Okay, but I mean, that's fine. So if you could say, look, everything points to the fact that it flows to the Gaussian fixed point, and then the rest.
So the operator part of it you can make more precise using these symmetries.
Okay. You said that T bar 2 pi is IH. T bar 2 pi IH is rolled out, right?
No, I didn't say it. Oh, for sigma.
Just from h going to
Just
h.
h going to minus. So sigma is. So what I'm trying to say is e to the 2 pi IH is like sigma sigma. It's like a bond energy. That's all I'm saying. So in fact, e to the 2 pi IH is exactly the coarse-grained version of the dimer density at a finite wavelength. Okay. Because 2q is the same as minus q, and 3q is the same as v.
You want spin to go to minus spin and h goes to h plus. That's one.
Okay. Alright, so let's go.
If you haven't even gotten to your talk, I suggest we do it like that.
Let's fix the date when you can make it work.
Okay.
And if you don't mind.
I don't
Is
mind.
tomorrow the same time?
Yeah, tomorrow the same time we will.
I'll try to make it. Go ahead.
Okay, then maybe we can, at a natural point, can you begin?
We'll stop at
I'm sorry for harassing you.
That's fine. I didn't expect to get to the end of the talk. I expected to get to the statement of it. Okay. So I've given you this background. And now, let me just say that I'm going to work on, actually, now is a good time to stop. I'll start here.
Yeah, it was great.
Now is a good time to start. So tomorrow I'll start here. And I'll tell you what's the problem.
Fantastic.
That will be a good starting point.
Very good.
Wait. That's questions. ICTS questions?
No, I think they have left for that.
No, I can see Loka.
Loka's there.
Unless the frame is full. ICTS?
No, I think that's old. They've shut off. Oh, no, they're.
Hi. Do you have questions, Loka?